Thank you.
Okay, thank you, Maru. Good day, everyone. Welcome to the fifth episode of the ANENT Webinar Series 2025. And this is our 19th since we launched the series in 2023. I am Ana Elena Conjares from the Philippine Nuclear Research Institute of the Department of Science and Technology, and I am your moderator for this webinar. Nuclear technology, particularly through the application of ionizing radiation, has emerged as a transformative tool in addressing the global challenge of plastic waste. This innovative approach addresses the limitation of conventional recycling methods. Today's webinar, we will feature the ionizing technology applications for sustainable plastic recycling in the Philippines. And to discuss this very important topic, allow me to introduce you to our speaker, Dr. Madrid, or Dr. Jordan Madrid, is a career scientist too and the head of PNRI's Chemistry Research Section under the Atomic Research Division. His field of expertise is in the areas of radiation chemistry, radiation processing, and polymer chemistry. He has close to 48 publications under his name. Dr. Madrid obtained his Doctor of Philosophy in Science and Technology from Gunma University, Japan in 2018 and his Master of Science in Chemistry from the University of the Philippines, Diliman in 2015. His current research projects include two national funded projects, post-radiation reactive exclusion of plastic waste, and the second project is nuclear materials exploration and recovery. He has also two IAEA projects. One is a national project on strengthening national capacity in radiation processing for product development and scale up. And another is a regional project on reutilizing and recycling polymeric waste through radiation modification for the production of industrial goods. So without much further ado, I am honored and proud to present to you our speaker today, Dr. Jordan Madrid. Dr. Jordan.
A pleasant afternoon, everyone. Okay, allow me to share my screen. Okay, and it should be in presentation mode now. Okay, so let's begin. First and foremost, I'd like to thank Ellen for the very kind introduction. And of course, the organizers, the Asian Network for Education and Nuclear Technology, ANENT, as well as the organizer for this event, for giving me the privilege and the opportunity to share a topic which is very close to my heart. And I also extend my warm greetings to all the participants, to our audience, who may be joining us from different time zones. Good morning, good afternoon, perhaps good evening to some. So I am Jordan Madrid, and as Ma'am Ellen mentioned, I am a researcher at the Philippine Nuclear Research Institute of the Department of Science and Technology. And today, allow me to present our work, the output of our research, our study on the application of nuclear and ionizing radiation technologies in plastic recycling. So this is an area of research and development and innovation that not only advances scientific innovation, but also directly contributes to addressing one of the most pressing environmental challenges of our time, plastic waste management. So the results that I will share with you are products of a collaborative project funded by the Department of Science and Technology, particularly the Philippine Council for Industry, Energy, and Emerging Technology, Research and Development, or DOSDP SHIRD. And the project is also strongly supported by the International Atomic Energy Agency through the New Tech Plastics Initiative. And this endeavor would not have been possible without the valuable contributions of our partner institutions. Their logos are included in the slide. First, is our sister agency, the Industrial Technology Development Institute, ITDI, our private company counterpart, Envirotech Waste Recycling Incorporated, and of course, the Polytechnic University of the Philippines. Okay, here's the outline of my presentation. I will begin with a brief introduction to the Philippine Nuclear Research Institute, the country's center for nuclear science and technology studies. Next, I will share the motivation behind this work, why plastic waste is such a pressing challenge, and how radiation technology, how ionizing technology offers innovative and sustainable solutions. From there, I'll present the research and development outputs of the project, where I will highlight the results and the practical applications that we developed together with our partners. And finally, I will close with a summary of the key points of this talk. So first, about the Philippine Nuclear Research Institute, or PNRI. Um, this is a snapshot of the PNRI compound. As you can see, one of its most recognizable landmark is this big dome, which used to house the Philippine Research Reactor 1, the Philippines' very first nuclear reactor. And so the institute itself was originally established in 1958 as the Philippine Atomic Energy Commission, and later it became what we know as the PNRI. Our mandate is twofold. First is to promote the peaceful applications of atomic energy in areas such as health, agriculture, industry, the environment, and second, to ensure the safe and secure use of this utilization of atomic energy. Now, right now, there are also important policy developments, I would say, like the bill creating the Philippine Atomic Energy Regulatory Authority, or PhilAtom, which has already been ratified in the Congress. And this will separate the promotional from the regulatory functions at PNRI. So it's now awaiting the signature of the Philippine president. Now, this slide shows the organizational structure of the institution. Within the Philippine Nuclear Research Institute, research activities are primarily carried out under the Atomic Research Division, which serves as the main research arm of the institution. So one of its 6 sections is the chemistry research section, as you can see here, where our team belongs and where much of the work I will present today has been carried out. So within the chemistry research section, we have 2 main teams organized according to research focus. The first is the radiation processing group, which studies radiation chemistry and explores how ionizing radiation can be applied in the synthesis and modification of materials. Now, the other group is the radiochemistry group, which focuses on the use of radionuclides and, and its application in various fields, from health to environmental studies. So for today's presentation, the results I will be sharing come primarily from the work of the radiation processing team, as this work directly relate to plastic recycling and materials development. Now, let me share some background on why we are implementing this project. What's the motivation behind the implementation of this project? So the Philippines has often been cited or labeled as one of the world's major contributors to marine plastic pollution. And so this is not just a matter of scientific interest for us researchers, for us chemists, for us scientists. It is also a moral obligation to find solutions that are both efficient and effective. Now, one of the root causes of the problem is the low recycling rate, which, according to a study published by the World Bank Group, the Philippines recycling rate it only stands at around 28% in 2021. So the remaining 72% of used plastics end up in landfills, or worse, leak into rivers and oceans. Now, the question is, why is this recycling rate so low? There are many issues, but one of the key reasons is the poor thermomechanical properties of um, recycled plastics. And this is primarily because once many of these plastics are processed, they no longer have the strength or quality needed for most applications, making them unattractive to industries. But here at PNRI, my team would like to view, and perhaps not just at PNRI, there are other research institutions, other research groups worldwide. But here in the Philippine context, my team would like to view the reported 72%, the remaining 72% unrecycled plastics differently. We can choose to view this 72% as garbage, as waste that then clogs our landfills and pollutes our waters. But my team chose to reimagine it as a valuable resource, a potential feedstock for new industries, if only we can find the right interventions. Now, another way to look at the issue is through the long-standing pattern of linear plastic consumption. So basically, we manufacture plastic products from virgin feedstock and then use them for the convenience that they bring to our daily lives. Afterwards, they are discarded, and most of them end up in landfills or, as mentioned earlier, inevitably, some of them leak into our waterways and oceans. So this model of take, make, and then dispose, or the linear plastic consumption, has been the norm for decades. But as we all know, our natural resources are finite. Continuing this linear cycle is simply not sustainable, both for the environment and for future generations. And so, instead of looking at the used plastics as waste or trash, my team chose to see them as valuable feedstock, something that we can modify and reuse for a wide range of applications. Now, the idea is to keep these materials, these used plastics, in circulation as long as possible, thereby reducing our dependence on virgin feedstocks. And of course, helping to conserve our finite natural resource. And this practice, in essence, is what we call the circular economy. And there are many pathways to make this possible. With simple sorting, many used plastics can actually be directly reused. Now, through mechanical recycling, we can reprocess them into secondary raw materials for manufacturing various plastic products. If we do chemical recycling, plastics can be broken down into simpler molecules like monomers or other valuable chemicals, which can then serve as feedstock for producing new plastic products. And finally, because plastics are inherently energy rich materials, they can be converted into energy through oxidation reactions or thermal treatment, producing the electricity that can be used to power our homes. So across all of this recycling and treatment methods, nuclear and ionizing radiation technologies can play a vital role. It can enhance efficiency, it can improve product quality, and it can enable processes that would otherwise be difficult, if not impossible, to achieve. So through nuclear and ionizing technologies, we have the ability to transform the bulk materials, the nature of various materials, including plastics, under moderate conditions and without heavy reliance on chemical reactants. Now, traditionally or conventionally, this could be done by, or this is being done by industries by adding chemical additives. They can improve the quality of recycled plastics by adding chemical additives. So this could be effective in the short term. However, this approach can also create another problem. That is, the materials become harder to recycle again, limiting their long-term usefulness. However, radiation processing or the use of ionizing technology offers a different vision. With ionizing technology, we can achieve the same improvement in strength, durability, and overall performance, but without introducing extra chemicals. And the result is a cleaner, greener process that keeps the plastics more recyclable and eventually more sustainable. And this is what I would like to emphasize. For industries, it means being introduced to new high value products made from recycled plastics, products that can compete with and hopefully in some cases outperform those made from virgin materials. And for students and young researchers, who I hope some of our audience are um, part of, it is an opportunity to work on a premier technology that not only advances science, but also makes a tangible difference in the effort against plastic waste and in shaping a circular economy. So, with that introduction, I would like to present our project, the Post Radiation Reactive Extrusion of Plastic Waste, or what we call as the PREX Plastic Project. So, the main goal of this initiative is simple yet ambitious, I would say. That is to transform discarded plastic wastes into robust and durable materials through the intervention of ionizing technologies. Now, how do we do this? We start by using electron beam irradiation technology to irradiate selected plastic wastes, which then induces specific modifications at the molecular level. Now, the irradiated plastics are mixed with unirradiated plastics and then extruded and molded into various shapes and forms. Afterwards, the resulting materials are rigorously tested for their thermal and mechanical properties to ensure that they meet the standards required for real world applications. However, beyond the laboratory, the team also have a bigger vision. Together with our collaborator, the Envirotech Waste Recycling Incorporated, our dream is to see our Prex product used in house and building construction materials, an area where strength, reliability, and sustainability truly matter. And I believe that we are getting close to this dream. With the recent developments in the project, which I will be sharing to everyone with later, we can already begin to see the potential of the Prex to make a tangible impact, not only in advancing material science, but also in building a more sustainable future for our communities. And so, to ensure a more holistic approach, we built this project through strong partnerships. We are working closely with the Industrial Technology Development Institute, Envirotech Waste Recycling Incorporated, and the Polytechnic University of the Philippines, with vital support from the IAEA and DOSTP Shared, and also partial technical support from QSC Takasaki in Japan for specific aspects of the project's implementation. Now, for us, securing the commitment of these organizations has truly been one of the key milestones of the project. It shows that addressing a challenge as complex as plastic waste requires not just science, but also collaboration across research institutes, industry, government, and international partners. Now, I would also like to share with everyone the New Tech Plastics initiative of the agency. It is the agency's flagship initiative to address the global challenge of plastic pollution. And this New Tech Plastics initiative has been strongly supporting the implementation of not only this project from the Philippines, but also different projects all over the world. So it brings together countries and partners from around the world to fight plastic pollution on two fronts. So at the point of the source, by introducing technologies to improve plastic recycling. So as of the time that I have retrieved this from the IAEA website, 52 countries are developing recycling technology under this initiative. And the other front is in the ocean, where the bulk of the plastic waste, like microplastics, ends up. And when I retrieve this figure, 99 countries are participating in microplastic monitoring under the New Tech Plastics Initiative. So we are very much grateful to the agency for supporting these projects. Now, going back to the Prex Plastics project, let me share with you the project's story. So we are using the technology readiness level approach in this project. And in the interest of time, I'll skip over the first two technology readiness levels since those are mainly paper-based assessments and feasibility studies. So what we really want to demonstrate was the practical feasibility of producing stronger, more robust products from recycled plastic waste through radiation intervention. And to do this, we followed a systematic approach. We selected polypropylene and high-density polyethylene recycled polypropylene and recycled high-density polyethylene as our main materials. So this choice was made in close consultation with Envirotech to make sure that we would not only have enough feedstock for our experiments, but also that the materials would be readily available should we later scale up the production, which we already did in this project. So the recycled plastics were then irradiated at PNRI using a 2 mega electron volt electron beam. And after irradiation, the samples were blended, extruded, and compressed into specimen form suitable for mechanical testing. We then conducted a series of evaluations to study their characteristics, focusing on and mechanical, thermal, and other physical properties. So the results of these experiments, which I will show you next, provide very promising insights into how radiation can truly add value to recycled plastics. Now, one of the biggest challenges in plastic recycling, I think everyone knows this, is the heterogeneity of the waste feedstock. As many of you know, recycled plastics they rarely come in pure form. Their composition can vary greatly depending on the source, which makes it very difficult to achieve consistent properties in the final products. That is a challenge. Now, to introduce more control in our experiments, we try to source our feedstock from single batches as much as possible. And in that way, we could minimize variations and we can make more reliable conclusions. We then performed characterization studies to evaluate the material properties. And in this slide, I show to you some of the data, particularly from the differential scanning calorimetry test and the Fourier transform infrared spectroscopy test. So in the DSC data, the result, no, as expected, the results from these two tests are consistent with the known properties of the plastics. For example, in the DSC data, the recycled HDPE showed a melting point around 130 degrees Celsius to 140 degrees Celsius, while the polypropylene, the black one, melted at about 160 to 170 degrees Celsius. And that conforms to many published values for their melting points. So from FTIR, we were also able to confirm the characteristic chemical bonds of polypropylene and high density polyethylene. However, we also observed some extraneous peaks that we attribute most probably to impurities because these plastics are already recycled. So after characterizing them, we then use them for extrusion, molding, and then mechanical testing. And just like in any recycling projects, the goal of the team is to maximize the utilization of plastic waste. And to pursue this, we explored the possibility of blending our feedstock, polypropylene, and high-density polyethylene at different ratios. So for this stage, we chose the flexural strength as our initial response parameter because, as I've mentioned earlier, one of our our long-term goal is to develop materials for housing and construction. And in this application, in this field, bending resistance is an important property. So the results that we've obtained turned out to be very interesting. We observed a clear trend of increasing flexural strength with increasing polypropylene content, particularly around 80 to 90% polypropylene. On top of that, when we irradiated the blends, the whole composition of the blend at say 10 kilogray of those, the flexural strength increased even further. And so from these findings, we were able to make an initial estimate of the optimal formulation of our products. And this is a very important step moving forward to the subsequent phases of the project implementation. And of course, as scientists, we cannot stop at simply observing enhancement in properties or observing stronger materials. We need to ask why. What is the reason behind the observed enhancement? What is the reason behind the trend? And so we examined the effect of irradiating the individual components, the high density polyethylene and the polypropylene within the optimal blend that we've established in the laboratory. So what we found was quite revealing that the improvement could be largely attributed to the effect on HDPE, on the high density polyethylene. And interestingly, when HDPE is irradiated alone, we observed minimal changes in the melt flow index. So the melt flow index basically tells us how um, flowing or how viscous the material is. So the higher the melt flow index, the more the less its resistance, the less the resistance of the material to flow. So it's more flowable, it's more fluid. And we know that, in fact, polypropylene, when irradiated in air, tends to degrade. That's why its melt flow index increases with irradiation. However, for high density polyethylene, there is not a significant increase in the melt flow index with irradiation. And this is very important because during processing and manufacturing, the melt flow index is a very important parameter to determine the throughput of the manufacturing process. And so we made further studies, further tests um, for the irradiation of HDPE, and we asked ourselves the HDPE cross length during irradiation. And so we measured its gel content. However, we observed that there is minimal to almost no cross-linking. And this finding is very significant because, as a matter of fact, we don't want our HDPE to cross-link because cross-linked plastics are difficult, if not impossible, to recycle. Instead, what we hypothesize is that the radiation-induced branching in HDPE um, occurred during irradiation. And this branching likely improved the compatibility between HDPE and polypropylene, which could be one of the key reasons behind the enhanced flexural strength that we observed in the blends. Now, again, let me emphasize this point that our goal is not only to produce strong materials from plastic wastes, but also to ensure that they remain recyclable at the end of their life cycle. Because as I've mentioned at the beginning of my presentation, we want to keep the materials in the loop of manufacturing as long as possible to reduce our dependence on virgin feedstocks. So imagine this: if this product will soon be launched to the public, could be used by the public. Once a Prex product, a product of this project, has served its purpose, for example, as a building material, when it when it reached its end of life, it could be returned to Envirotech, to our private company counterpart, where it could be reprocessed and transformed into a new product. So this kind of circularity becomes extremely difficult if the material is highly cross-linked or if we rely heavily on chemical additives. And this is precisely why nuclear and ionizing technologies hold so much promise for plastic recycling. They allow us to improve material performance without sacrificing recyclability. Now, to continue, as part of the systematic characterization that we carried out in this study, because as I've mentioned earlier, recycled plastics are very heterogeneous, so we need to characterize them as much as possible. One of the parameters that we looked at was the density of the feedstock and of the different blends. Now, as many of you may already know, high-density polyethylene has a more linear structure, more linear polymeric or molecular structure compared to polypropylene. And that's why HDPE is generally reported to have higher density compared to polypropylene, which has a more branched structure. And so when we measured the density of our feedstock, for example, the HDPE and the polypropylene, including the OPP, which is the plastic waste sourced from Envirotech, the results were very consistent with what is already reported in the literature and also with the values typically used in industry. Now, earlier, we mentioned that electron beam irradiation at low doses did not lead to cross-linking in high-density polyethylene, but it could have resulted in some degree to chain branching. And in the next few slides, I'll show a simple measurement that I'll show how the simple measurement of density can actually provide evidence to support this claim. So one of the clear indicators is the change in density after electron beam irradiation. When chain branching occurs, so remember HDPE has a mostly linear structure of polymers, of molecules. And when chain branching occurs, whether it's short chain or long chain branches, it creates a more irregular molecular structure. And this irregularity makes it harder for the polymer chains to align and pack efficiently, which in turns lowers the density. And this is exactly what we observed. After electron beam irradiation, sorry, the density of the high density polyethylene it decreased from 0.967 to 0.958. And this is consistent with the idea that branching was introduced into the material. Take note, there's no cross-linking or minimal, very minimal cross-linking here as uh, 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 what we've proven when we did the gel fraction experiment. And the same was observed with the blends, like for the 9010 polypropylene high-density polyethylene, where the use of irradiated HDPE contributed to the lowering of the density. And even when we use OPP, which is the plastic waste sourced from Envirotech, we observed the same trend. And so the incorporation of irradiated HDPE still led to a reduction in density, showing that this effect is consistent, whether we start with recycled materials or with unprocessed plastic waste feedstock. And finally, when we look at a different formulation, so earlier I showed the results for 9010. This time, we also performed the test with 8020 polypropylene high-density polyethylene blend, um, which I will explain in detail later. We still saw the same effect, that the use of irradiated HDPE again contributed to a decrease in density. Of course, density measurements gives us a good initial indication of chain branching, but we are also exploring other techniques to further analyze this behavior in HDPE. And perhaps if I have another opportunity in the future, I will be sharing those results with you. Now, aside from density measurements, we also evaluated the water uptake of the samples after a 48-hour period. And the results showed minimal water absorption across all the specimens that we've tested. Now, this is a very encouraging finding, especially because we are aiming to apply these products in building and construction materials, where resistance to moisture is critical for durability and long-term performance. We also examined the morphology of our samples by taking detailed photographs, and shown here are the scanning electron micrographs of pure polypropylene as well as the blends 9010 polypropylene high density polyethylene. And for comparison, we compared the unirradiated, okay, and irradiated samples. So aside from 9010, we also measured or take a look at the photos of the another blend, 8020 polypropylene high density polyethylene, again unirradiated and irradiated. Now, if I'm not sure if the quality of the image is good, but when we look at the pure polypropylene sample, we see that its surface is relatively smooth and as compared to the blends. So if you look at the blends, at the polypropylene HDPE blends, whether it's 9010 or 8020, it show more complex surface features. For example, we observed hollow indentations and spherical protrusions. And these are often referred to as core shell or core skin structures. And this result in a noticeably rougher morphology of the blends as compared to pure polypropylene. And this roughness that we observed in the blends can be attributed to the presence of high-density polyethylene dispersed within the polypropylene matrix. And as expected, the effect is more pronounced in the blend containing more high-density polyethylene content, which is the 8020 polypropylene HDPE blend. So interestingly, when we looked at the samples prepared using irradiated HDPE, we observed a slight decrease in the number of the hollowed and protruded regions, suggesting perhaps that irradiation offered or improved the compatibility between the two components, leading to a relatively more uniform blend. Okay, so those are some of our findings in the laboratory. And after we were able to establish the optimal conditions at the laboratory scale, the next logical step was for us to test these findings at a larger scale. So, excuse me. And this transition from the lab scale to a larger scale is always a critical part of the process because it tells us whether the results that we see in controlled lab conditions can actually be replicated in a real production environment. And for this, we are very fortunate and we would like to thank Envirotech um, for allowing us to conduct our runs using their actual manufacturing lines. So, as in all our trials, initially, uh, earlier, I reported in the laboratory scale. Now, at a larger scale at Envirotech, the first step is to carefully characterize our feedstock. So, one of the most notable observation that we observed at this stage of the project was that the polypropylene, if you look at it, the OPP that we sourced from Envirotech, um, it was not completely pure. Now, this is expected, but the result that we've obtained is quite telling. It showed a measurable contamination by HDPE. And so at this point, we are investigating the possible reasons for this. It may be that the contamination comes from the equipment used during the collection or processing, or perhaps it it's reflecting something which is inherent in the raw materials that was used in the experiment. Anyway, I'd like to show some photos taken during the production runs at the Envirotech. This gives us a clear picture on how the samples were actually extruded and compressed at a larger scale. So the process begins with the plastic waste from Envirotech and the irradiated plastic waste at PNRI. Um, they are manually mixed to ensure an initial blending of the two types of plastics. After that, the mixture is fed into an industrial extruder, where inside the extruder, the plastics are subjected to elevated temperature and mechanical shear, which causes them to melt and mix thoroughly at the molecular level. So once the molten blend is prepared, it is then molded and compressed into the desired shapes. Now, the exact shape or form depends on the type of test that we want to perform afterwards. For example, could be flexural testing, compressive testing, or other mechanical and physical characterizations. Now, let me move on to the results of our test runs or of our trial runs at Envirotech. I won't go into every detail of the trial runs, but I'd like to highlight some of the key findings. First, we observed that the optimal blend identified from the large scale tests was different from the one that we had previously established at the lab scale test. And the difference was not very large, but it was noticeable. And this variation could be due to several factors, among which, for example, the reduced number of processing steps in producing one of the components, particularly the OPP, because in the lab scale, we use pelletized polypropylene. However, in the large scale, we use shredded plastic waste from collected by Envirotech. Another key difference is the type of extruder that we used during the trials. Now, what was truly encouraging, however, was the performance of the Prex samples that we've produced. In terms of flexural and compressive strengths, the Prex, the materials, the sample specimens produced by the Prex technology outperformed or has higher um, compressive and flexural strength compared to the company's current formulation, Envirotech's current formulation, and it exceeded that by more than 50%. This was a very satisfying outcome that we immediately communicated it with the president of the Envirotech, Engineer Lemon, because it directly supports one of the central goals of the project. That is to enhance the mechanical properties of the products made from plastic wastes, and to do so without the need for additional chemical additives. And to make sure that these results were not like due to chance only, we carried out 3 separate trial runs at Envirotech across different time periods, from June to August 2024, February 2025, and again, the last trial run, the third trial run, just last month, July 2025. And these multiple runs were designed to verify the reliability of the trend, the reliability of the process using different batches of plastic waste feedstock. And as you can see here from the data, the results have been remarkably consistent across all 3 periods for flexural strength and compressive strength of the samples produced. And I have to say that even I was pleasantly surprised by the reproducibility that we have observed here from the results. It is quite striking to see such consistent science-based evidence showing that the Prex technology can deliver mechanical properties that are not only improved or enhanced, but reproducibly, in a reproducible manner across different operating conditions and feedstock sources. Now, one of the important concerns when you think about the use of these plastic blends for outdoor applications is how they behave under sunlight exposure. In particular, we want to know whether the stiffness of the material changes significantly when it is subjected to heat. If the sample were to lose stiffness at relatively low temperature, then that would limit their use in practical outdoor settings. So to address this concern or this issue, our collaborators from ITDI, they performed a test using a dynamic mechanical analyzer, which will evaluate the stiffness of the samples at different temperatures. Particularly, we did it from 25 to around 80, more than 85 degrees Celsius. And the results were very promising. The elastic modulus, which tells us the material's ability to resist deformation, did not drop drastically when the temperature was raised to 85 degrees Celsius. And to put this into context, 85 degrees Celsius is well above the range of typical outdoor temperatures in our environment. God forbid that we will reach that temperature in the future due to climate change. Hopefully not. And this finding indicates that the samples prepared at Envirotech are able to retain their stiffness and structural integrity even at 85 degrees Celsius at elevated temperatures. In other words, they're robust enough to withstand real-world outdoor conditions without significant change in their stiffness. And similarly, the samples produced at Envirotech were also tested for water absorption. And just like what we had seen earlier, at the lab scale, the calculated water intake, as you can see here in this plot, remained very minimal. And this is important because excessive water absorption can compromise mechanical properties and to a certain extent, shorten the lifetime of materials, especially when we use them outdoors. And in addition, we carried out real-time aging tests. So here, the samples that we prepared last February 2025, we brought them back here to PNRI, and they were directly exposed to natural outdoor conditions, to sunlight, to rain, and even stormy conditions from February to July 2025, covering a span of about more than 5 months. And this kind of exposure test is valuable because it simulates the actual stresses, the actual weathering that the materials will encounter in real application, in real use. And the results are plotted here for everyone's appreciation. The compressive strength test that we've obtained remained very consistent across different testing periods. That one I mentioned earlier, showing that the performance of the blends is reproducible over time and over different feedstock used. And if you look at the results of the 5-month aging test, the last two bars, where we did uh, samples exposed indoor and samples exposed outdoor, um, we observed that their compressive strength did not change significantly compared to the values that we obtained from the earlier runs. So, in other words, despite being exposed for almost half a year to extreme sunlight in the Philippines, the months of April and May is very torturing because it's very hot here, and they are exposed to rain and storm conditions. Um, Despite being exposed to the natural elements, the structural integrity of the material was largely preserved, and that is evidenced from their um, consistent compressive strength. Now, the only noticeable change was in color, which we suspect is due to UV exposure. But aside from the surface effect, the strength of the samples remained relatively unchanged. And this is a very encouraging result because it demonstrates that the materials not only perform well initially, but they also retain their strength after real world weathering. And lastly, we also submitted our samples for flammability testing. The results showed, as flashed here, that the material possesses moderate flame retardant properties. And we want to further validate these findings and to give us a clear picture of the fire performance of the blends and help us determine whether we need additional modifications or treatments for specific target applications. And so, apart from the that we funding support that we are receiving from the Philippine government, this project is also being supported by the agency through the regional TC projects, coordinated research projects, as well as the New Tech Plastics Initiative. And in planning the next steps of the project, we are applying the Technology Readiness Level approach, or TRL approach, where we are being mentored by IAEA experts and also by the business development section of the Philippine Nuclear Research Institute. And so our target is, as you can see here, is to reach TRL 5, hopefully within the year. Um, and in addition to this milestone, we are planning the construction of a prototype house made partly from Prex products. We aim to accomplish this within the year, and this will not only serve as a demonstration of the Prex technology, but also as a concrete example of how plastic waste can be transformed into durable, useful, and sustainable products for housing applications. So to realize that, we are planning to construct a 24 square meters house. Um, it's a small house. Basically, it's for low-cost housing with parts made from the Prex products. And in collaboration with the Polytechnic University of the Philippines College of Architecture, Design, and Built Environment, and the College of Engineering, this is part of the design that they are developing. And it is a single-story simple house that will be built in the PNRI compound. And this is the proposed perspective of the prototype house. And we hope that that the actual build will start by September and be completed by October 2025. So we also attempted to perform a simple gate-to-gate life cycle assessment to with the goal of evaluating the carbon emissions associated with producing our Prex products. In this case, the Prex tiles. And what I'm showing in this slide are the system boundaries that we defined and used for the calculations. And the results of our simple gate-to-gate life cycle assessment showed that in producing Prex tiles, it leads to an emission of around 17 kilograms of carbon dioxide per square meter of product. Now, to put this number into perspective, the number, this value falls roughly in between the reported figures for conventional ceramic tiles, which is reported in the published data to emit around 15 to 16 to 25 kilogram carbon dioxide per square meter of ceramic tiles. And what is perhaps more insightful is the breakdown of these emissions. When we look at the relative contribution of these steps, it, it is clear that the majority of the carbon footprint comes from the electron beam irradiation and the extrusion stages. In the Philippines, we are using a lot of coal plants. And so that is used to power of course, for example, the electron beam facility. And so it contributes a lot of carbon emissions. And this is an important finding because it tells us exactly where improvements can be targeted. And so let me summarize the project at its current stage. The Prex plastic project, I would say, clearly demonstrates the potential of using ionizing technology as a tool to enhance mechanical plastic recycling. So through this approach, we are steadily working our way toward achieving technology readiness level 5. And what we have accomplished so far, the output that I've presented to you, has only been possible because of strong collaborations with government support, with international partners, and with private industry such as Envirotech. And looking ahead, one of our next immediate steps is the construction of the prototype house made from Prex products that will allow us to further evaluate the applicability of these recycled materials in actual housing construction. So taken together, these efforts that we've taken so far, that we've made so far, move us closer to the vision of transforming plastic waste into durable, sustainable, and useful building materials. So before I wrap up, I'd like to briefly introduce another project that my team at PNRI will be implementing in the near future. I know teams from Malaysia and Indonesia, our colleagues from Malaysia and Indonesia, are actually already doing this research, which is radiation-assisted pyrolysis of plastic wastes. So in this project, or in this study, we want to explore how ionizing technology can be used to complement or even reduce the external heating normally required in pyrolysis. And we'll be starting this project very soon, and I look forward to sharing the results with all of you in future presentations, or perhaps my colleague will be able to share the results of this study. So let me end by saying that as we move forward, a more sustainable future, the use of recycled plastics in housing and construction is more than just an innovative solution. It is a responsibility that we owe to our planet, that we owe to the generations, the future generations that will inherit it. And together, we can turn what was once discarded, what was once thrown away, into the very foundation of our better tomorrow. So I would like to acknowledge the team members who are integral to the implementation of this project. And before I give the floor again to Elena, I'd like to share to everyone the International High-Level Forum on New Tech Plastics, which will be held here in the Philippines on 25 to 26 November 2025. And this high-level forum on New Tech Plastics aims to showcase the relevant achievements of the New Tech Plastics Initiative participating countries and advancements in radiation-based technology. It also would like to facilitate the exchange of knowledge and good practices, emphasizing on how nuclear technology can accelerate progress, among other aims of the high-level forum. So please keep this in your calendar. Perhaps you can also participate in this high-level forum. And with that, please reach out if you have any questions or potential collaborations. Thank you very much for your kind attention. Back to you, Elena.
Thank you, Dr. Madrid. You have really come a long way from 2022, I think, when you started these efforts, right? So it started
That's right.
in
From
2022.
2021.
2021. Okay. So, and I also remember before that you were a little bit hesitant to join, but now now from the presentation that we had made, you could really see how we have already reached that TRL5, almost TRL5, right? So, and also I'm so happy to know from the presentation the results that you have gotten from the experiment, from the laboratory, and also from the Envirotech itself plant. So for our audience right here, if you have any questions, could you please raise your hand so that I can acknowledge you, or you can also write in the chat box. So currently, I don't see any questions from the chat box, and also I don't see any hands raised. So may I ask Jordan, Dr. Madrid, regarding the high-level forum that will be happening in November, could you please expound more on it? Who will be coming over, or who will be participating, and what are the various, what will it feature? Both the technical aspect, and it's also the political format of the program.
Uh, okay, for the thank you for that, Elena. For the International High Level Forum on New Tech Plastics, from the last communication that I've received from the organizers, I think this one will be attended mostly by they've invited ministers from different countries. As for what these countries are, I'm not well informed yet, but they are going to invite ministers, vice ministers from various countries all over the world to attend this, where the advancements in the New Tech Plastics Initiative will be discussed. And it is not just about the advancement in the technology. I think they're also there to discuss some of the technology transfer, some of the business aspects of the New Tech Plastics Initiative. Because as I think, presented or shown in my presentation, that we need to elevate, to enhance our effort on um, transferring the technology, making it possible for the public to use them, taking them out from the laboratory, and giving them to the public or to the private companies for them to commercialize it or for them to produce it for public good. So so aside from the technical aspect, there will be this business aspect, and I think some policy aspects also of the that are relevant to the New Tech Plastics Initiative. Yeah.
Thank you, Dr. Jordan. So I still don't see any hands, but maybe I don't know if it was so technical at the early part of your presentation. But I think what we got from your presentation, especially for the Philippines, is that it looks promising, especially as you know, we have so many. I think many of our countrymen, Filipinos, really need to have low cost housing. So this kind of materials coming in from the project that will be manufacturing from the recycled plastics would really be a good material, or good materials to be used to for this low cost housing.
That's
So
correct. That is a dream, Elena. And
okay.
if I can also share, I attended a forum yesterday, and there's also this um the Department of Education, the classrooms that they're building, the public works under the
Mhm.
Department of Public Works and Highways. I think they're also looking into sustainable products or sustainable materials for constructing like public works, infrastructure for public works. And we are also targeting that, but this time through Envirotech, because once we transfer the technology to Envirotech will be the one to negotiate with these types of applications.
Yes. So
So
yeah.
yeah, from low cost housing also to infrastructure development.
Thank you. So I think I have someone here from the chat box who would like to ask a question, Mr. Sahid Mahmood. Yes, you may ask your question now, please. You may open your microphone and ask your question. Mr. Sahid? Oh, because he put there that may I ask a couple of questions. So, Mr. Sahid, you may open now your microphone. Can you hear me? Anyway,
I'm not sure if
so
they're allowed to.
I
Mr.
Maru.
Zahid, Mr. Zahid, do you hear me? I have changed your role
Okay,
and allowed your microphone, the camera as well.
okay, also okay. Thank you, Maru.
Don't worry.
Okay, so while waiting for Mr. Sahid, I'd like to answer the question of Miss Dr. Maung Maung Tan. Yes, if he could or she, if she's asking if he could get a soft copy of the presentation. So yes, we will provide you with a copy. Maru-san will provide you with the link to where you can get a copy of the presentation. So I think Mr. Sahid is asking for you to unmute his mic. Could you please try, Mr. Sahid?
Okay,
Oh,
I also changed his role from the guest to presenter as well. Can you check Mr. Zahid? Now you can use microphone and camera as well.
Mr. Sahid, I think you can now use your microphone. Please try.
Hello.
Okay, thank
Hello,
you.
Yeah, I can
everyone.
hear you. I can hear you.
Yes, we can hear you now. So please, you may ask your question now.
Can you hear me, everyone?
Yes, we can hear
Yes.
you.
Okay, that's fantastic. Thank you very much for a fantastic talk and very informative talk from Dr. Jordan F. Madrid. That was a very useful talk. And unfortunately, I joined in the middle of the talk because of some time confusions over here. So my question relates to some chemistry, as Dr. Jordan was discussing. At slide number 16, he mentioned about the FTIR peaks, and he also informed that there's some branching that went on the blends, right? So my question is that there were some peaks which were indicating some impurities within those recycled polymers. So do you think that is there any particular impurity that is playing its role in branching of these blends? So, or you have you studied these impurities in detail that they might have played their role for specific kind of properties which were produced in this mixture? Okay, thank you for the question, Dr. Zaid. Very important point that we need to clarify. First, in the FTIR, actually, we did not observe the branching from the FTIR, but as perhaps most of you know, that polyethylene is a cross-linking type of polymer under when we irradiate it. However, after we've irradiated it and then checked for its gel content, which is the basically the basic methodology to check for a cross-linking of any polymers. We observe that there is very minimal to almost no cross-linking. That's why that led us to our hypothesis that perhaps there is chain branching. And our hypothesis was actually supported by the change in the density of the material after we've irradiated it. Now, as for whether we've observed or we have studied in details the impurities, because I've mentioned that the FTIR showed extraneous peaks. Actually, we did not, because we number one, we believe that the impurities are present there because they are processed by the industry for specific applications. That's why those impurities, or perhaps they have been um, included in the plastics final form during the synthesis of the plastics at the polymer plant. And so we did not um, studied in detail the impurities which are present. But what we focused on are the bulk properties. But this is something that we would like to look into deeper when we go and when we studied the materials in that we've used for this project, because it is imperative, and I believe that it's imperative that we um, characterize the material as much as possible. So whether these impurities could have caused the enhancement, perhaps we tested the hypothesis or the technology across different time periods and across different feedstock, OPP feedstock, and we observed the same trend. And so we are thinking that perhaps this is really due um, to the modifications that we did in the molecular level through irradiation of the high density polyethylene, and then it's blending with polypropylene. But yeah, we are still the project is still ongoing, and perhaps we are going to look into more details about the impurities, about the the impurities which are present in our feedstock in future works. So thank you for that question, Zaid, Dr. Zaid.
Thank you, Dr.
Thank you very
Jordan.
much. Thank you very much indeed for your nice answer to me. And I hope that I'll be continuing listening to your lectures in future as well. Thanks indeed, once again.
Thank you for the kind words. Thank you.
Thank you, Dr. Sahid. And may I know if other people here around, or do you have any questions? More? So I think I don't see any raised hands. I'm not sure if the microphones of the other participants who are here are working. So, Mr. Marisan, have you allowed all microphones to be unmuted? Or only those who would like to ask questions? Or do they have to ask permission first?
Yes, I think so.
Okay. So, but anyway, if anybody who would like to ask questions and is not able to use their microphone, you might please write in the chat box so we could open it for you.
And perhaps Elena and Ma'am Ellen and Mr. Maru, they are still synthesizing or developing their questions. But
Yes.
yeah, anyway, they can also reach me through my email. They have clarifications about the presentation, because I think the ANAD is among our Asian it's an organization of Asian countries, if I
Yes.
right. So I think
Yes.
most of them here are also part of the project of the RAS 1031. Some of them are part of the RAS 1031 projects, and I'm sure that we have opportunity to share these findings through different platforms. And if you have questions, please feel free to reach out, clarifications about the project or even potential collaborations, because we would like to, as part of the project of the RAS 1031 project, one of the, I think what we are promoting is the exchange of knowledge, of information about this laser nuclear ionizing technology, for not just for plastic recycling, but in general materials modification, for, of course, for various beneficial applications in general. So thank you.
Yes, thank you, Dr. Jordan. So I think Mr. Marisan has already put the link where you can get the materials. And as Dr. Jordan said, you could also reach him. Yeah, on the screen we have right now his email address. So you may just send him an email if you need more clarifications from from his presentation, especially after you have read it again. After you get a copy of his presentation. So this time now, I would like to thank everyone for coming, and most especially, I would like to thank Dr. Jordan, because maybe some of you from outside the Philippines wouldn't know that today is really a non-working holiday for us, but Dr. Jordan still accepted to present for this webinar series of ANAN. So I'd like to thank you, Dr. Jordan Madrid, again, Dr. Jordan, for coming and for presenting the results of your project on new tech plastics. And as you said earlier, that you're welcome again to present to our webinar series when we have more or update the future results of the project. So, and again, I would just like to share, as I said earlier, I because I started with you in starting this project, I was already with you, so I knew that you were a little bit hesitant to join the project because you were not so confident. But as you have said also during your presentation, so it's really a group effort. A group effort is better than just one person doing anything, right? So with a private partner, immediately at the start of the project, that was really very helpful, and also the support of the other DOST agencies, national funding, but most especially also the support of the IAEA. So we have what we have right now, what we have already developed, almost ready for transfer to be commercialized. And all of this, and this progress really, and this achievement is really thanks to all those, the collaborators that you have. So we hope to see you again in our 8th webinar series and for more updated of the progress of your project. Thank you all, and thank you, Dr. Madrid, again.
My pleasure, Elena. Thank you, everyone.
So,
Thank you very much, Dr.
and hope to see you again next month for our 20th webinar series for Thank you and goodbye.